Okay, so we've talked about permutations and combinations. Just to review that. An ordered arrangement of elements is a permutation, and unordered arrangement is a combination. And we also defined the binomial coefficients. The binomial coefficients n choose R, in this case, which were used to count combinations. Okay. So as a simple question, if you have n things and you want to choose all possible combinations of R things out of n things, the number of combinations, they're called R combinations. The number of R combinations of n is n choose R. That's what we call this. That's how we remember it, because n choose R, that we're trying to choose R things from n. And the way we calculate it was given here. So it's n factorial divided by n minus r factorial times r factorial, or n falling factorial r. So that's you get an r permutation, you put them in order, then you remove the ordering by dividing by r factorial. Okay, so those were the binomial coefficients. So now let's move on to a little bit of a more general case, which is called multinomial coefficients. So where do binomial coefficients come from? Where they come from is what's binomial? Bi means two. So binomial is saying we're trying to choose n choose r, means we're trying to choose r things from n. And so there are two categories. That's what binomial means. The two categories are you're either in the group we choose, or you're not in the group we choose. So either yes or no. Okay. So that's where binomial comes from. In some cases, we're not talking about just two categories. We might have three categories. It might be, you know, you might have, in politics, you might say, who are you going to vote for? It could be candidate one, candidate two, or undecided. Okay. So now you have three categories and you want to choose so many to be for candidate one, so many to be for candidate two, so many to be undecided. That is where we're going to need to use what's called multinomial coefficients. Okay. So let me give an example first. So the example is that we're trying to split a group of people into teams. Okay. There are 11 children and 3 activities. Okay. And activity A requires 6 participants. Activity B requires 3 participants. Activity C requires 2 participants. Okay, so 6 plus 3 plus 2, that's 11. How many ways are there to split the class? So how many ways are there to split the class among these activities? Okay. So what we're going to do is we're going to say, okay, I need to pick 6 students to go into activity A, 3 students to go into activity B, and then whoever is left is the 2 that are left are going to go into activity C. We don't care. There's no ordering here. We're picking six people, putting them in. There's no ordering there. Okay. So how many ways does it do this? Well, We actually know how to do this based on everything we've done so far because we can, it's kind of, it's similar. It's not, it's actually very similar to the poker example. And we can use binomial coefficients and the multiplication rule. Okay, so how do we do that? Well, we're going to, okay, so I want to do it two different ways, right? So let's say, just to prove that the ordering doesn't matter, but let's start by saying, all right, we have 11 students to start, and we're going to pick 6. Let me actually do this. Let's number the students. So we have 11 students. Okay. And let's color. How we going? Okay, let's call A. I don't like that. Let's do this pink. Let's do this green. Let's do this blue. Let's pick blue. Okay. Okay. So what we can do is we can say, okay, first we're going to pick 6 participants to go into group A. So let's pick. Oh, I skipped one. Oops, come on. So let's say we end up picking 1, 2, 3, 4, 5, 6. Okay. So we're first going to say, okay, you're either in A or you're not in A. So that's binomial. You're either in A or you're not in A. So first of all, we're going to first pick A, 6 for A, then pick 3 for B, then pick 2 for C. Okay. Okay, so first we're picking 6 for A. Choose 6 for A. How many ways are there to do that? Well, there's 11 to start. From the 11, we pick 6. Okay. Let me organize this a little different. Okay. So 11, we pick 6. 11, choose 6. Okay. And then what? Then we want to pick 3 for B from the remaining. Well, how many are remaining? Well, once we've picked these 6, we need to then pick 3. Well, how many are left? There's 1, 2, 3, 4, 5. And we pick 3 from the remaining. Okay. So there's always 5 left. No matter who we pick to go into group A at first, there's always 5 left. 5, choose 3. There's always 5 left, so we know that we can multiply 5. That's 5, choose 3, no matter who gets picked. So multiplication rule. And then whoever's left is whoever's left. That's it. So they have to go into group C. Choose 2 for C. 2, choose 2. Now what's 2, choose 2? It's just 1, right? It's only one way to pick 2 people out of 2 people. Anyway, if we do this, we get 4,620. Okay. Now let's do it a different way. Just to make the point. Okay. So I'm going to do this again. 1, 2. Okay. But this time what I'm going to do is I'm first going to pick, just say we pick 2 for C. We pick C first. then we pick B, and then we pick 6 for C. So 6 for A. So we pick kind of in reverse order than we did the first time. Okay. So first we're picking C. So we're going to pick, let's say, these two. How many ways are that you, so now we're saying two people are going to go into group C. Okay, we have 11, and you're going to either be assigned to C or not be assigned to C. So what is that? We know that's 11, choose 2. Now, no matter who we pick out of 11, there are how many left to now pick for B? There are 9 left. So multiplication rule. 9, choose 3. We have nine people. We're going to assign 3 of them to B. And now, however many are left, there's 6 left. They all get assigned to A, so it's 6, choose 6. So whoever's left, they're automatically assigned to A. Do the math on this. 46, 20, same number. And you can try this in any order you want. You're going to get the same answer if you do it right. Why? Well, the reason is, let's think about how we're doing this. Okay, so this is what's going to give us ultimately a multinomial coefficient. What is the multinomial coefficient? So given K labels, so in this case, the labels are A, B, C, and N balls. So we put this in terms of labeling balls, but of course we can apply that concept more broadly. The number of ways to label N K balls, N eyeballs, I'm sorry, N sub eyeballs with the label I for each I from 1 to K. So for each label that we have. Subject to the condition that the sum of these ni's adds up to n. What is that? Well, it's something called the multinomial coefficient. So in this case, it's going to be n choose n1, n2, up through nk. And how do we define that? Well, that's what we're going to call it. Let's try to think through it. Okay, so we have K labels, N balls, and we're trying to label the N balls so that we assign N sub 1 of the balls with label 1, N sub 2 of the balls with label 2, up to N sub K of the balls with label K. We define this thing and this multinomial type of coefficient. This has no meaning for us yet. We have to figure out what it is, okay? What is it? Well, let's apply the same logic we did up here, okay? We're just doing it a little bit more abstractly, okay? There's N balls to start. Let me assign label 1 first. So for each of them, at step 1, I'm going to either assign label 1 or not assign label 1, right? So we can kind of see that we start at step 1, we assign label 1 or not. How many are left? So there's n at step 1, n1 are getting label 1, n minus n1 are not getting label 1. No matter which balls get labeled, there's always n minus n1 left. So this is the binomial choice So step one is n choose n1. Now at step two, multiplication rule, there's always n minus n1 left. We assign label 2 to n sub 2 of them. So how many do not get labeled 2? N minus n1 minus n2. Right? So multiplication rule means this is n minus n1, choose n2. Right? And then what's step 3 going to be? It's going to be n3 of that we have this many left, n minus n1 minus n2, n3 of which are labeled 3, n minus n1 minus n2 minus n3, of which are not labeled 3, and so on. So it goes all the way down to n sub k. At the end, we're going to have n sub k left. But let's just, so we're going to have n minus n1 minus n minus k minus 1, and nk minus 1. Choose nk. Okay. So that's our answer. And we could have done this in any order, and you have to convince yourself you're going to get the same answer, but we'll see why we'll get the same answer by actually working out. So I'll shrink this up a little bit. Oops. Okay. So we're going to work out, do a little simplification here. So what is n choose n1? N choose n1, remember, is n factorial, n1 factorial, n minus n1 factorial, times n minus n1 choose n2. Well, that's n minus n1 factorial divided by n2 factorial, n minus n1 minus n2 factorial. So on and so forth, down to n minus n1 minus n sub k minus 1, choose nk. That's going to be n minus n1 minus n sub k minus 1 factorial. Choose, or no, divided by n sub k divided by n minus the whole thing, everything. All right. So let's do a little cancellation here. So what we can see, right, is this here on the bottom cancels with this here. Similarly, this will cancel with the numerator of the next, and so on and so forth. This will also cancel with the numerator of the previous. And so this goes away. This goes away. All of these go away. And what we're left with is, and then what is this? Let's ask what this is. Well, this is n minus n1 minus n2 minus n3 all the way up to minus nk. Well, remember we've assumed that the sum of all the ni's is n. So n minus that sum is just 0. So this is 0 factorial. And remember, we define 0 factorial to be 1 by default. So that's going to go away because 1 doesn't affect anything. So what does all of this come down to? Is all you're left with is n factorial in the numerator divided by n1 factorial, n2 factorial, product, all the way up to n sub k factorial. So that's your multinomial coefficient, okay? And what you can see is that this is commutative. This does not depend on the ordering of the n sub i's. If I were to write n choose nk minus 1 down to n1, as long as those numbers are the same, the values are the same, the product in this denominator is going to be the same because you can multiply things in any order you want, okay? So this is going to be called multinomial n choose. So multinomial n choose n1, n2, nk. It's called a multinomial coefficient. Why is it called this? Because remember how we define binomial coefficients here in terms of you have a binomial expression. Binomial means you have two variables, x and y, in this case, x plus y raised to a power. So multinomial is raising k variables to a power. So if I have x1 up to xk raised to the power n, then the question is, okay, what is the coefficient of the term? So I'm going to end up if I actually work all this out, what I end up with is I have terms that look like this. x1 to the power n1 times up to xk to the power nk, such that each one of these ni's is bigger than or equal to 0, and they add up to n. Okay. Each one of these terms gets a coefficient. What is that coefficient? That coefficient is exactly the multinomial coefficient that we just defined. So that's why it gets that terminology. Okay. Okay, so this is how we count combinations where we're putting groups, we're putting individuals, or we're classifying objects into some fixed number of some number of groups, arbitrary number of groups. Doesn't have to be two. And we derived this actually from first principles because we first knew how to classify things as yes or no. And then classifying things into more than two groups is just a bunch of sequential yes or no decisions. And we use the multiplication rule. So that's how we do, that's called multinomial coefficients. So next time, so that's the multinomial coefficient. And we still have a little bit more combinatorics left before we get into probability models, and we'll take care of that next time.